Well, now we're going to move on to the 16th lecture, which is part 2. Lecture of 15 and 16 was so large that I divided them into 2 separate lectures. The whole issue of parameter estimation and tracking. In part 1, we discussed parameter estimation and single target tracking. And now in part 2, we're going to be discussing more broadly the tracking issue. And one thing I wanted to mention is that between breaks, Eli Bruckner's book is Tracking and Kalman Filtering Made Easy. And at the end of this lecture, Eli gets its credit because a fair amount of the material, with his permission, I'm using in this and the next part of the last 2 pieces of the lecture. Okay, so let's move on with the lecture material. Again, we've got our block diagram of the radar. And at this time, if you haven't gotten used to it, I don't know when you're gonna. And here we are down to the last section. We've done the parameter estimation. If it was a single target tracker, we looked at that in detail and the different ways of doing single target tracking. And now we're going to look at multi-target tracking. And multi-target tracking is going to have a number of different issues related to it. We're going to have an introduction to it, and then we're going to spend a good deal of time on just what the tracking process logically is. And then we're going to look at a number of different techniques that will be smaller in size, but very important in their use. And the introduction is a good time to, for me at this point to say it, as I look back on my years in radar, there are many of us who have skills in hardware. Many of us have skills that are analytical. And a truly good radar systems engineer has both, and that is very rare. If you look through the journals of the IEEE's Aerospace and Electronic Systems Journal, and you just did a list of all the papers on tracking, you'd find a majority of them on theoretical tracking issues with limited data sets, where a tracking technique hasn't been employed for months or years in a specific radar and then evaluated. There's more of an emphasis on the formalism and the math and less on, in personal opinion, than on the physics if you've lived with trying to make a radar work with a regular radar system. And then in this section, correlated misdetections and correlated false alarms, I'm going to point out that issue to you. Always when we're doing analytical calculations, it's easy to say the noise is Gaussian and the false alarms are random across the screen. And that's not the case most of the time. And that's the reason radars have problems with lots of false alarms. And then I'm going to talk about another detection tracking technique, which is called track before detect, which really means assemble an awful lot of data, of detections at low threshold where we have a lot of noise, and use hypothesis testing to see if there are sets, very heavy computer burden, of detections that will follow a track nicely at the expected velocity and state vector that you expect the target to be, and that way you could run the radar at a higher false alarm rate, but see targets that are smaller. And so that's the genesis of the track before detect technique, and we'll go over that, and then we'll look at integrated multiple radar tracking, and then summarize. So now let's move on to the introduction. And as I always like to show you, multiple target tracking radars, these all do that. Here's the Russian flap lid radar. It's S300. It's a lens array. Back here is a horn, and there are ferrite phase shifters in this face. And this was taken by Martin Rosenkrantz. I believe he's an Austrian. And he goes around, I think it's a hobby, to many different air shows in Europe where the Russians set up at the air shows their air defense systems they'd like to export. And he has on the web an absolutely beautiful collection of images of different Russian air defense radar systems. So I sent him an email and asked for permission, which I got, to use that. Here's a picture of Patriot, which looks similar, and the ASR-9. We saw that in the last lecture. And here we have a slotted waveguide airborne radar, and of course the rotating antenna of an AWACS array inside this large Boeing aircraft. So we've got multiple target tracking radars that perform surveillance in lots of different shapes and sizes. And what are the algorithms? What's the general block diagram of what you do? You know, we're going to get rid of look at that next. But this is what you want to do. You want to take a whole bunch of detections, which we have here, over a 10-mile. It doesn't even say whether it's range or kilometers, but it could be either one. But excuse me, it doesn't even say whether it's nautical miles or kilometers, but it could be either one. This is just for an illustrative example. And you can see just to the eye that a lot of these detections, they're somewhat noisy, but yeah, your eye says they follow a track. And these two, and here, and here, and here, and over here. And ideally, instead of putting a dot, you could put a number or an alphabetic symbol, A, B, C, D, E, F, G, H, I, J, K, and that would tell you that they all happened along the consecutively in time. You have that information in the computer. And these are the observations. And so the tracker receives new observations every scan, and here are the observations from many scans. And then what we want to do is we want to find out what where the tracks are. And in this case, they're denoted that here the true position, we have new tracks that are short, that may be just random sets of noise that just barely exceed threshold. That's probably what most of the red is, new tracks. Some of them may evolve into longer ones, but these blue tracks are clear, existing tracks, and they end after a while. So new tracks are initiated, existing tracks get updated with this kind of data, and obsolete tracks are deleted from the track file. Track file, think of that. You know, just a big memory device that has a list of all the tracks and all their attributes. And now we're going to look in detail at the tracking process, which will give us that kind of a result. Oh, by the way, I want to go back just for a moment and point out, we want to know as accurately as possible the state vector, x, y, z, t, x dot, y dot, z dot, and t, the state vector of the target. And if it's got acceleration, the x double dot, y double dots, and z double dots. We want to know the state vector of each and every track, which tells us where it is in space and where it's going. And if it's accelerating or decelerating, it'll have double dots on x, y, and z. Well, that stands for, obviously, time derivative. So now let's look at the tracking process. And here it is. This is really a generic block diagram of pretty much all tracking radars in a general sense. There'll be little deviations, but as we're going to slowly go through this, we have detection threshold crossings, which I showed you earlier. From one scan of a radar, you could have many detections in Doppler space. They can be you detect the target in range azimuth Doppler space, and what you want to do is consolidate them into one point, which characterizes the location of that point in range and azimuth and elevation and observable space at a given time, amplitude, and it can also give you a quality. Are the detections made up of just one single threshold crossing, or is it a whole band of threshold crossings that you'd expect from a strong target? So what we want to do is take those detection threshold crossings and consolidate them into raw target reports. And then what we do generally is send those raw target reports into an adaptive area constant false alarm rate processor that is used most oftenly in radars that work in the atmosphere to deal with breakthrough clutter, with bird migrations, with down in south, the bats can leave the cave for an hour. There may be an extremely there may be an area over a hill that has a highway that goes over that hill, but that highway is high enough and far enough away that automobiles at 60 miles an hour are constantly going over that hill and in the beam. And so you might want to censor that one little deep place or not initiate new tracks and adaptively set a threshold on that area. And given the physical, I call it humanity of the geographic space around you. So an area adaptive CFAR is an essential part of the radar, I'd call it pre-tracking process. And what we do this for is so that we don't overload the track files and try to initiate on a giant flock of birds that are coming up from Cuba as they do every spring for an hour to the Florida coast. So we take these filtered now raw target reports, and then we send them into a function which is called track association. The first thing you want to do is you want to say, is this part of a track we've already got? You know, you see down here we've got a track file. And we want to say, does this associate with other tracks in the track file? And if the answer is yes, and we're going to go into detail, by the way, on every one of these boxes, by association, have we gotten just boom, 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 and now we have another detection right here, just where it should be. You know, do we associate? Yeah, that's the one. There might be multiple ones. Which one do we choose? That's going to go on in this process. And if it's yes, we want to update the track file. And we also want to predict after we update, send that information in to the track update so that we can predict further in the next scan where to expect the next detection. If we don't associate that raw target report with an existing track, non-associated reports will go into track initiation. And I'm going to explain how we do that. And then they would go into a track formation algorithm and then go into the track file, which has the state vectors of all the tracks in file and the predicted positions ahead. A lot of mathematics in this. Now, once you have this state vector in the track file, I'm going to talk about how this is altered by phased array radars at the end. But you can see that once you've done the association, if we associate, we update the track files. If there's no association after a number of scans, we terminate the track, or we might coast the track 1 or 2 or 3 till the probability that if it really was there, we'd have seen it. Then we terminate the track like it landed at the airport, or it flew behind a mountain. And we'll pick it up on the other side of the mountain. And new tracks would go into track formation and then onto the track file. So this is the overall block diagram. Now, when you have this track file, the upper portion, where from about here up, is the way you deal in a track-well scan radar. But with a phased array radar, we have a great deal of flexibility, and that we have a radar scheduling of tracks where we can send out pulses at any time where we want to. So right after we initiate a track, we can send out 2 or 3 confirming pulses immediately to reinforce our knowledge that it is indeed a track moving uniformly in XYZ T space. So for phased array radars, we have an update track monitoring system, and then we'll control the radar scheduling to send out at different times. Say we have a track, a target in track, and we've designed it that we like to get it's a missile tracking radar. There we're going to want to get a nice quick update. You want to get an update, might be every 1/10 of a second. So we'll schedule the radar, if it has a very fast speed, as a missile might, to go every 1/10 of a second, bang away. Or if it's a slower track that needs less of an update, just, update at a slower rate if its velocity is lower. Or if it's accelerating, you could send out batches of tracks to find which way it accelerated. So there's a great deal of flexibility that I wanted to point out, and in this complex radar scheduling controller that phased array radars can have. But this block diagram here works quite well on dish radars that do track-well scan. And if you look at a simplified view of these different these different tasks, it really blocks down to fewer blocks. And there are really these 4 functions. And we're going to look at each of these 4 functions in detail. First, we have the new observations, where we have detection of reports and range azimuth. We can measure over time the range rate from range cell to range cell, the different detections, and get a value of that. Or we could directly measure Doppler if the radar is capable of it, azimuth, elevation, time, etc. And that will go into association. And then we have existing tracks get updated, and the updates will be used for prediction and for association at the next scan. And if it's non-associated, we initiate a new track, and then we update the disk file. I made it as a disk, but it's really a computer memory these days. And then we keep updating the track, or we terminate it when we get no more reports that the track is there. And so, taking my ad hoc words, we have in blue these 5 things we do. Track association. We associate new observations with existing tracks. Track initiation. We initiate new tracks on non-associated observations, and usually 2 or 3 scans before we initiate a track. Track maintenance, we update. We do a smooth, we call it a filtered estimate of the target's present position. We'll go into the mathematics of that a little bit later. And we predict ahead, using the same mathematical techniques, a new estimate of the target's state on the next scan based on our present information. We update it. And then we terminate tracks that are missing new observations for a given number of scans. So the goal of the tracking process is to take these raw detections from the radar and output a state vector, certainly amplitude information, and obviously from the track we can get certain track quality information, like track life. Has this been in track for a significant number of scans? Has the amplitude that we'd expect a target to have? Does it occupy just one range azimuth Doppler cell, or a number of them that would be more likely if it's a relatively short range and you're looking for aircraft and it's not a low observable aircraft? And we want as few, if any, false alarms. 2 exclamation points, because that's always the dream. But we want as few false alarms as we can with the technology and our intellectual skill in making this tracking and designing and implementing this tracking system. Okay, now I used this view graph before a little bit to point out, make a different point. And it shows you for an airport surveillance radar, this is one beam width, and these are the exact target detections from 4 coherent processing intervals. And these are one PR. There were 2 different PRFs. One was about 120% of the other, and that was to take care of blind speeds, because this radar is ambiguous in Doppler velocity. So we saw it in this coherent processing interval. In the center, we saw it at both coherent processing intervals, and also in 2 range cells. It was overlapping, and the bigger circle just means it was larger. And here we see it in 2 range cells. And so often the target, as I say, may produce many adjacent threshold crossings, and we usually use adjacency and range angle and Doppler as a criteria for grouping the cluster of detections. And the sets of threshold crossings and their amplitudes are then used to interpolate to get the best value of the observables. For different cases, the different methods are the best. We can use a weighted average. We can fit the data to the expected angular beam shape for angle, the pulse response for range, or the Doppler filter shape for Doppler velocity measurements. And here are 2 graphs, spectrum of a single range gate that was probably about 5 miles away from an airport surveillance radar that was located on Katahdin Hill at Lincoln Laboratory. And what we did is we just sent out, I believe it was 1,028. If you count the number of lines, you will know the number of pulses that we put through a it might be, is it 64 or 120? I think that's a little too much for 128. I think we put it through, there were 64 pulses, and or 128. I don't want to count them on the fly. And we put them through a weighted we held the beam of the radar fixed, and we looked at where aircraft would be taking off and landing. And we did this to measure the spectra of aircraft, the Doppler spectra. And this is in relative dB, and the noise level is marked in each case. And this was the spectrum of a commercial airliner. And you know a commercial airliner has fans on their engines, their jet engines, that go around at very high PRF, extremely high frequencies. And what we're seeing here is just plus or minus 60 knots. We sent the pulses out at about 1 kilohertz, and approximately. And we see here a bump where we get the main signature of the target. But we also see a lot of Doppler threshold crossings above the noise level. And that is that the ambiguity in Doppler all folding down. And that's why these targets were seen in many Doppler cells. But here is where the target really is. Now over here, when we have a two-engine propeller aircraft, we see the modulation of slower moving propellers. And here we see the much higher main lobe from the plane itself. So you can see that in radars, the aircraft Doppler spectra can give you detections, in many cases, when you're flying and it's folding down at different Dopplers other than the main lobe if you're in close.